Hey there, everybody. Welcome back. We're looking at Stokes' theorem in Calculus 3. Let's just dive right into it. I got the formula up top in case you forgot it from the last video. We can do the curl of f dotted with n for the surface integral instead of doing the line integral of f dot dr. So we're going to find f dot dr where f is negative y squared in the x direction, x in the j direction, and z squared in the k direction. The curve we're going to use is the intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1, which I have pictured over here to the right. The cylinder x squared plus y squared equals 1 is the center, or the axis is the z axis. And so we're making the cylinder up around that. Y plus z equals 2 kind of slices that in a wedge going downward. And we're looking at this. Where those intersect is right along here. So that's where we're looking. That's our curve. Okay. So we want to use that curve. To use Stokes' theorem, we need the curl of f. So let's find the curl of f. And we've got, when you work it out, you got 1 plus 2y in the k hat direction only. Okay. This kind of lines up well with our Stokes theorem, our Green's theorem. This is the same thing effectively as curl of f. Is it really? Curl of f dotted with k? Looks like it. dg dx minus df dy. Yep. Everything else zeroes out because there's no components for it. So we have, that's our surface integral. We can switch this to polar and evaluate it in polar. Make sure when you're doing it, you switch everything in the function to the polar coordinates when you do it, and insert the correction factor r. And we go through it, recalling that sine or cosine of 0 to 2 pi gets you 0. But when you get through it, you're going to find out that you get pi as the final answer. And that's what we're going with. And it's worth pointing out, in case you forgot, f dot dr, what we're working on here, this was the work in physics. So if you're looking for a physical explanation, this is work of moving a particle around this field. What we're doing is effectively the surface we're going to use, we're projecting it down onto this surface down here. So we're going to do stuff in the XY plane. We've done this projections in other sections before, and we're going to do it in future ones. I thought maybe pointing out it in the book and showing it to you there might help. So let me pop it up. They show in the book, going around this figure over here, if you're going around a plane and it's got 4 sides, to do the line integral, we'd have to integrate all 4 sides doing the line integral, or instead we can just do the surface integral. And since it's at an angle, the surface is weird. Rather than rescaling everything, what we're doing is projecting it onto the XY plane. We're going to choose the plane we want to project it to. And that seems like the easiest one to do. So keep that in mind. F dot dr is work. I'll look for a particle around a field. Let me put it back up. Work is F dot dr for a particle around a field. And instead of doing the particle going around the curve on a field, we can do the curl of f dotted with n for the surface. That was our first example. We got pi. What does this tell us? The field is not conservative, because to do a full loop around the thing and we did not get a value of 0 means that it is not a conservative vector field. Just keep that in mind, tying this all together. That's it for this one. We'll do another one in the next video. Peace.